Jai Hind, myself Pushkal Kumar Shukla, Assistant Professor in Computer Science Department at AKGEC Engineering College, Ghaziabad. Today I will discuss subject Theory of Automata and Formal Language, code BCS 402. It is applicable to BTech 4th semester students. Today I will discuss about the grammar and Chomsky classification. Objective of this topic is to understand students' role of grammar in generation of language, distinguish between ambiguous and non-ambiguous grammar, and how to write a CFG and the regular grammar, and simplify the CFG. All these are the objective of this topic. Now come on the topic grammar. What is grammar? So grammar is a set of 4 tuples. A grammar G is a set of 4 tuples Vn, Vt, P and S, where Vn is set of non-terminals, Vt is set of terminals, P is a production rule and S is the start symbol. For example, S equal to ASB. This is a grammar. So this is a grammar where S is set of non-terminals. Small a, this is set of terminals. Small b is also set of terminals, and this is set of non-terminals. And this is a production rule. And S is the start symbol. So grammar is consists of the 4 tuples Vn, Vt, P and S. Generally, non-terminals are represented by the capital letters and terminals are represented by the small letters. And here S is the start symbol, so it is start from the S, so this is the start symbols, and all this is the production rules. So this is known as the production rules. So grammar is classified in 4 ways. Chomsky classified grammar in 4 types, that is type 0, type 1, type 2 and type 3. 4 classifications are there, that is to be recommended by the Chomsky. Type 0. Type 0 grammar is also known as unrestricted grammar, and it is accepted by Turing machine. There is no restriction in the grammar. So the production rule which is written in this type 0, there is no restriction. So this type of grammar is accepted by the Turing machine. Type 1 grammar is also known as context sensitive grammar, and it is accepted by linear bounded automata. Next, type 2 grammar, that is known as the context free grammar, and it is accepted by push down automata. Now next, type 3 grammar, that is known as the regular grammar, and it is accepted by the finite automata. So type 3 grammar, that is finite automata, means it is accepted by the DFA and it is accepted by the NFA. Deterministic finite automata and non-deterministic finite automata. Like regular grammar, like 0 ke power n, 1 ke power n. So this type of for n is greater than equal to 0. So this type of grammar is accepted by this finite automata. Push down automata, that is context free grammar, like a ke power n and b ke power n, and n is greater than equal to 0. N is greater than equal to 0. So L equal to this type of language is accepted by the PDA. And Turing machine, like a ke power n, b ke power n, c ke power, any type of algorithm, any type of problem can be solved like a ke power n, b ke power n, c. That is to be accepted by the Turing machine. Yes, a plus b, yeah, a into b, all this type of problem can be solved by the Turing machine. Now come on the type 0. Type 0. Type 0 grammar is also known as the unrestricted grammar, and it is also known as recursively enumerable grammar. It is accepted by the Turing machine. This type of grammar, the production is of the form alpha to beta. Alpha to beta where alpha is element of Vn union Vt का star Vn and Vn union Vt का star. So where alpha equal to Vn plus Vt या Vn union Vt star Vn union Vt का star and beta equal to Vn union Vt का star. Just for example, where Vn is set of non-terminals या variables and Vt is set of terminals. This is for example, A is AB equal to BAA. So this is alpha and this is beta, and alpha having this is Vt, this is Vn, this is Vt, this is Vt. यानी Vn union Vt का star and Vn, and there is no restriction at the alpha and no restriction on the beta. So and this is beta is Vn union Vt का star. So it may be epsilon. Vn union Vt star means it can be epsilon. Yeah, like this. A equal to this S oblique A. So all this type of production comes under the type 0 grammar, and it is accepted by Turing machine. There is no restriction in the production rules. There is no restriction. We can write like this. Type 1 grammar. Type 1 grammar is also known as context sensitive grammar, and it is also length increasing grammar or non-contracting grammar. Type 1 is of the production alpha to beta is said to be type 1 grammar if mod alpha is less than equal to mod beta, where mod alpha is Vn union Vt ka star, Vn union Vt ka star, and beta is Vn plus Vt plus. Yani epsilon is not allowed here. This is for example ASAB. Here we see this is alpha, and mod alpha equal to 4 and mod beta equal to 5, and here we see mod alpha is less than equal to mod beta. So this condition is going to satisfy here. So type 1 grammar, the production is of the form alpha to beta, where mod alpha is less than equal to mod beta. Here alpha equal to 4 and beta equal to 5. So this condition is going to satisfy, and alpha is element of Vn union Vt star, Vn union Vt star. It is composed of it is composition of terminals and non-terminals, and composition of terminals and non-terminals, and beta is this. Now come the type 2 grammar. Type 2 grammar is also known as the context free grammar, and it is accepted by push down automata. In type 2 grammars, the production is alpha to beta is of the form where alpha is element of Vn, set of non-terminals, and beta is element of Vn union Vt ka star. So and also mod alpha equal to 1. It means ki left hand side the length should be 1. Here we see the mod alpha, this length is mod S equal to 1, mod A equal to 1, mod B equal to 1. So the necessary condition is alpha should be less than equal to beta. This mod alpha is less than equal to mod beta. This condition is also going to satisfy it, and also mod alpha equal to 1. Mod alpha equal to 1. But in case of type 1, only this condition is going to satisfy. Only this condition is going to satisfy. This condition is not necessary important. Not necessary. So here S equal to AB. So this length is 1. This length is 2. This length is 1. This length is 3. And this length is epsilon is also there because the star is also there. This length is 1, this length is 2, and epsilon is also there. Type 3 grammar. This grammar is also known as the regular grammar, and this type of production is accepted by the DFA and NFA, finite automata. So the production is of the form A equal to AA, yeah, A equal to capital A. So this is known as the right linear grammar, right linear, and this is a left linear, left linear. So a grammar is said to be right linear if it is of the form A equal to AA. If production is from this A equal to capital A equal to small a, so this type of grammar is accepted by finite automata and it is known as the regular grammar. Yeah, A equal to AA, left linear, yeah, A equal to A. So this is left linear grammar and it is also accepted by the finite automata. So a regular grammar is of two types, right linear grammar and left linear grammar. So this is example of right linear grammar and this is example of left linear grammar. Regular grammar, right linear grammar, A equal to AB, A equal to A and A equal to epsilon. So here this is non-terminals, this is terminals and this is non-terminals. So this is a right terminal, right linear grammar. Yeah, there is a non-terminal followed by terminal, yeah, non-terminal followed by epsilon. So this type of grammar is known as right linear grammar. Similarly, A equal to BA, this is non-terminals in left hand side. So yeah, A equal to A and A equal to epsilon, this is a left linear grammar. So all these are the regular grammar and it is accepted by the finite automata, DFA and NFA. Now come on the transition for conversion of regular grammar into finite automata. The transition for automata are obtained as follows. For every production A to AB, if there is a production A to AB, we make epsilon A equal to B. If there is a production, A to AB, so we make transition function A to A and state is A and we give input as a small a and then it shifts to the state B. So like this. For every production A to A, make transition function A small a equal to final state, and for every production A to epsilon, make transition function A epsilon equal to A and A will be the final state. So three rules are there while converting a regular grammar into finite automata. For example, convert this following grammar into finite automata. So S equal to AA. So it starts from the state S. We give input A, and there is a state A and it is labeled from S to A and give input A and it is labeled S to A. Again S, B, B, yani if it starts from the state S and it goes to the state B and input is B and it labeled from S to B like this. This is S equal to B, B and this is S equal to A, A. Now A equal to AB, so it starts from the state A and it goes to the state B and arc is labeled from A to B and input is given as A. This is A equal to A and B. A equal to small a, so A is goes to the final state. In this case we see like this. If there is a production A to A, make transition function A to A and final state. So it goes to the final state. This is the final state. From A state, if we give input A, then it goes to the final state. So this is A equal to A like this. B equal to small b capital B. So it starts from the capital B and we give input B, then it goes to the state B. So this is B equal to BB. Again B equal to small b, so it starts from the state B and it goes to the final state after giving input B. So this is the finite automata of the regular grammar as given. Now convert following FA to regular grammar, right linear grammar. Now very important question which is asked in the AK2 examination many times. Convert following finite automata to the regular grammar, right linear. So start, how to write? Start, this is the start state and this is the final state. Double circles are the final states and this arrow marked is the start state. So S equal to A and A. This is the, we write S equal to A. S equal to BB. So we write like this, S equal to BB. And right linear because right terminals, non-terminals are in the right hand side. So this is a right linear grammar. Again A, this A equal to BC, B and C, like this. And A equal to AS, this is given AS. B equal to AC and B equal to BS. C equal to again this, C equal to AB and C equal to BA. And since this is the final state, so we write epsilon, we add epsilon transition in this. So this is the regular grammar, right linear for this finite automata. So this is the way to write a right linear grammar of this finite automata. Now the question comes many times, convert the following finite automata to regular grammar left linear. So for this, what we have to do? We have to reverse start state into the final state, and so what we do here is start state to the final state. So make this final for left linear and final state to the start state. So make this arrow like this. And arcs is reversed. This is reversed by this, and edges should be reversed. Direction of edges should be reversed, and make start state to the final and final to the start state, reversing by this, and we write then right linear of this and again reverse it and we get left linear. So by this way we can convert a finite automata to the left linear grammar. Now context free grammar. Now context free grammar, a grammar is said to be context free grammar if production is of the form alpha to beta, such that alpha is element of Vn, yani set of non-terminals, and mod alpha equal to 1, and the beta is element of Vn union Vt ka star. This, for example, if you write S equal to ASB, and S equal to A. So here we see this is set of non-terminals, alpha set of non-terminals. Capital letters generally represent set of non-terminals. Small letters are used for terminals. So this is composition of terminals and non-terminals, terminals and non-terminals. So this is beta Vn union Vt star. Again, this is terminals and this is non-terminals. So left hand side should be non-terminals. Left hand side should be non-terminals. And mod alpha, the length of this should be 1. So this is CFG, context free grammars. And this type of grammar is known as type 2 grammar. And it is accepted by push down automata. Push down automata. So a context free grammar consisting of finite set of grammars rules is a quadruple Vn, Vt, P and S, where Vn is set of non-terminals, Vt is a set of terminals, and P is the set of production rules, and S is the start symbols. For example, this S equal to Bs. So here we see production rules S equal to Bs. The length of this S is 1, and this is terminals and non-terminals, composed of terminals and non-terminals, and this is non-terminals. So this is condition actually, and this is also a non-terminals and it is composed of terminals, and the length of this non-terminals on the left hand side is 1. This is also 1. So condition is going to satisfied that is required for the context free grammars. Again we see this grammar, this length is 1 and this is non-terminals, this is terminals, this is terminals, this is non-terminals, this is non-terminals, length is 1, and this is terminals, terminals, non-terminals, and S equal to epsilon. It means कि Vn union Vt star is there in the left, in the beta part. So in this epsilon should be also there. So this production is also acceptable in context free grammar. Thank you.